Hello and welcome to another lecture by Engineering Safari. And today we'll be talking about the DC and AC analysis of MOSFET, which is a metal oxide semiconductor field effect transistor. So this is the second module of analog electronics, and it's a direct continuation of the previous one, which was DC and AC analysis of bipolar junction transistor. So I'm expecting that everyone who is watching this has already watched that and has all the concepts in that clear, because that would make this chapter very, very short, because most of the concepts are the same here. Most of the circuits will be the same with very minor differences. So instead of going for another 3 hour lecture, I'm just expecting that everyone watches that lecture and comes back to this one, which would make this one easier to understand as well as a much shorter lecture. So, with that said, let's see what are the topics in this chapter and how they are different from the previous one. So, first, of course, we'll have an introduction to this transistor, that is MOSFET, and how it's different to the transistor that we spoke about in the previous video. Then we'll again talk about DC biasing. So unlike the previous one where we spoke about multiple different types of biasing and direct current, we just have one type here, the voltage divider bias. So we'll talk about how that circuit is simplified and how we find input and output characteristics in voltage divider for MOSFET. And then, just like we had in BJT, we also have the load line here where we have to plot the Q point for ideal functioning of the resistor. And after that, we speak about MOSFET capacitances. So unlike BJT, where we just had two capacitances between the transistor junctions, we have a lot of capacitances here, and we'll talk about each one and the formula required for all of them. Then, obviously, the rest of the chapter is very similar to what we had in the bipolar junction transistor. We talk about cutoff and transit frequency, then the board plot, the region for which amplification is optimal, the mid frequency response, the high frequency response, low frequency response, and how each capacitor actually affects each each type of frequency. So all of the responses are actually the exact same. Like the shape of the board plot is the same. The internal capacitances affect your low frequency, and the external capacitances, which are the bypass and coupling capacitances, they affect your high frequency response. All of this is, I mean, I just said it the other way. The internal capacitances affect the low frequency, and the other ones affect the high frequency. So we'll talk about that in detail when it comes. I'm sorry for that confusion. So all of those things are the exact same. The only thing that changes is the name of each junction, and with a few minor changes, which we'll talk about as the topic comes. So with that said, let's talk about what a MOSFET actually is. So MOSFETs are actually of two types. The first type being the depletion, and the second type being an enhancement type. So, like you can see here, let's take an example of a N channel MOSFET. So, an N channel MOSFET has a N doped source and N doped drain, along with the majority of this part being something called the substrate, which is made of p-doped semiconductors. So what happens in a depletion type is that this channel here is actually already made, right? So what is a channel? The channel is basically a sea of electrons that allows majority charge carriers to flow from the source to drain. So if the channel is absent, basically there is no way the current can actually flow from the source to drain. So what actually happens in a depletion type is the channel is already made and we apply a negative voltage to the gate. So upon applying negative voltage to the gate gets a negative charge. So the sea of electrons that I just spoke about, right? They get repelled away. So slowly, as you go on increasing the voltage applied to the gate, the sea of electrons completely disappears and the current flowing from source to drain becomes zero, right? So that is the depletion type. And what we have in enhancement type is the exact opposite, right? So here we do not have the channel at the beginning, so there is no current flowing initially. So then what we do is we apply a positive charge to the gate. So now what happens? The gate gets a positive charge and that attracts all the negative charge carriers present in the body of this MOSFET. So all the electrons which are present throughout the substrate, all of them get attracted to this gate. And what that does is it forms this channel of electrons between the source and the drain. And that channel acts as a path for conduction, a path for current to flow from source to drain. So that is the enhancement type of MOSFET. So throughout this, and also obviously there are N channel and P channel MOSFETs. So if the source and drain are N doped and the body is P doped, it's called an N channel. And if the body is N and the other two are P doped, then we call that a P channel MOSFET. So depletion is of P and N channel and enhancement is also of P and N channel. So throughout this chapter, we'll only talk about N channel enhancement type MOSFET. So you don't have to worry about anything else. So how the circuit diagram for this looks like this. We are only going to talk about N channel enhancement type. So that is something like this. So this is connected to the drain. This is the source. And this here is the gate. Right. So like we had three terminals in the BJT which were collector, emitter and base. So similarly we have three terminals here as well. A gate, a drain and a source. Right. So all of these are very similar to their BJT counterparts. A gate is similar to the base. The source is similar to the emitter and the drain is similar to the collector in BJT. So these are uh, these are the basics of what is actually going on inside the MOSFET. So there are three. There is something called the threshold voltage, right? So what is this? What does this threshold voltage signify? It signifies that the channel has been fully formed and now you have a path for conduction. So let's say we apply a very small positive voltage to the gate. That means some of the electrons do get pulled, but the amount of electrons that are here is not good enough to form this channel. So we need to increase the positive voltage that is applied to a certain amount. That threshold is what we call the threshold voltage that is denoted by Vt. So as long as the gate source voltage is greater than the threshold voltage, you will have current flowing from source to drain. And if it's lesser, then there is no channel, so there is no flow of current. So the first reason that we'll talk about is when the gate source voltage is lesser than the threshold voltage. So here you have no channel and therefore you have no current. Then we have the linear or triode region where the gate source voltage is greater than threshold voltage. So that means you do have a channel and there is flow of current. And the second condition here is that the drain source voltage is lesser than the difference between VGS and VT, right? So for the linear or triode region, we have a formula for drift current, which is mu n Cox into W by L into V overdrive into VDS. Okay, so here V overdrive is always the difference between VGS and VT, and this W by L that we have here is known as the transistor aspect ratio. Aspect ratio. So this tells us the ratio between the width and length of the transistor. Cox is the oxide capacitance, and so yeah, that is those are the constants here. So this ID is though I've written the formula here, it's not very significant to most of the questions because most of them come from the saturation region where the drift current is significantly different. But this is just the formula in case uh, they ask something related to the linear or triode region. So then lastly we have the saturation region where gate source voltage is obviously greater than the threshold voltage and the drain source voltage is greater than the difference between gate source and threshold voltage. So this is called VOV or the overdrive voltage, right? So in saturation region, the important factor is that the drain current is independent of drain source voltage. So that is now it's given by half into mu and Cox into W by L into VOV square, right? So here basically we write mu n into Cox as Kn dash, where, where Kn dash is called the process transconductance parameter, and then we have half into Kn dash into W by L as K, where K is the conduction parameter. Okay, so this formula is very important and it comes up in all the numericals. So in any numerical, if there is need for usage of drain current, unless specified that it's in the triode region, you just stick with the formula which is given here. Okay, so these are the three main regions of operation. So now let's see how a common source amplifier looks like. So like I mentioned, the source is similar to the emitter in BJT, right? So since we only spoke about common emitter amplifier, we only look at common source amplifier here. So this is the voltage divider bias that we had, and instead of VCC, we have VDD, we have RD, which is the drain resistance, then we have RS, source resistance, and then we have two resistors, R1 and R2, right? So R1 is always equal to 2 into R2 when we are talking about this particular amplifier. Okay, and then since everyone has already completed the BJT lecture and they know how we simplified a voltage divider bias, we'll just directly apply that here. We'll use Thevenin's theorem and simplify these two resistors. That will give me VG is equal to R2 into VDD divided by R1 plus R2, and Rg is given by R1 parallel to R2, right? So here R1 and R2 are usually pretty large, They're always in kilo ohms or mega ohm units. Okay, so with that said, the main difference here that makes a MOSFET different from a BJT is that in the BJT we assumed IB to have some current, though it was almost zero for almost all calculation purposes. We considered it to be significant enough. However, in the MOSFET, the current that flows through the gate is completely zero. Like there is all the current that flows through drain flows straight through the MOSFET into the source. So that means the current flowing here is equal to the current flowing here, because you know that the current here is zero. So that means current through drain, which is, let's denote it with ID, is equal to current through the source. Let's denote that by IS. So we have ID is equal to IS and IG is equal to 0. So now let's try and simplify this. So if we for the voltage at drain, right, we can see there is a potential drop across this resistor. So I can write VD as VDD minus IDRD, right? So that is the drain voltage. Now, if I apply KVL on the entire output side of the loop, I'll get VDD is equal to IDRD plus VDS. VDS is the potential difference across the drain and source, and then I have IS into RS. However, we know that IS is equal to ID, so we can directly write this as ID into RS. So I have VDD is equal to IDRD plus VDS plus IDRS. So I take ID common from here, and then I get RD plus RS is equal to VDD minus VDS divided by ID. And similarly, I can write ID is equal to VDD minus VDS divided by RD plus RS. Right. So here again, like we did for VCE and IC max, here I need to see the value of ID max and VDS max, because I need to plot it on the load line, right? So ID max is given by VDD divided by RD plus RS. So when ID max is 0, VDS is 0, right? So then when VDS is max, is at its maximum, then that means ID is equal to 0, and we have the value for that as VDD. So this is exactly the same as the BJT, where we had VCE, and like I mentioned, the source is the same as the emitter and the drain is similar to the collector. And here we had VCC, now we have VDD, and so it's the same. It's almost the same thing. The only difference was that instead of the base current being of any significance, the gate current is going to be exactly 0. Okay, so with that said, let's have a look at some questions. Okay, so this is done. Yeah, so let's take the first question. I'm given that K, that is the conduction parameter, is 50 milliampere per volt square. The threshold voltage is 2 volt. VDD is given as 15 volt. RD is 470 ohm. Okay, so now I need to find RS, I need to find R1, and I need to find R2, and it's given to me that Vg is equal to 1 by 3 VDD. Okay, so this is the question. So now let's get started. We'll try and find everything that is given here. So the first step is there are a few things few approximations which we always take here. So the first one is R1 is equal to 2R2, and the second one is VD is equal to VDD divided by 2. This is another operation this is another approximation that we take, and this does help us in solving questions when the data given is inadequate for us to solve it. So yeah, so that is the first concept that is actually going to be applied here. Since we do not know the voltage of any of the terminals, we try and find one of them. So VD is VDD by 2. That gives us 7.5 volt. Okay, so now we have VD as well as RD. So we can find drain current as VD by RD, and that gives us 7.5 divided by 470. Okay, so that is 16 milliampere. Okay, so this is the value of ID. So now we have an equation for drain current, right? So the equation for drain current is given by K into VGS minus VT whole square. So now I know ID is equal to 16 into 10 to the power minus 3. I know that K is also equal to 50 into 10 to the power minus 3 because it's milliampere per volt square. And then I have VGS is unknown, VT is given as 2, right? So from this equation, I can find out that VGS is 2.6 volt. Okay, so now I have VGS and I also have VG, which is given by 1 by 3 into VDD, right? So 1 by third of 15 is 5 volt, right? So like the name suggests, VGS is the potential difference between the gate and the source, right? So that would be VG minus VS is equal to 2.6, and we just found VG to be 5, right? So 5 minus VS is equal to 2.6. Wait, right. So this is correct. So VS is given by 5 minus 2.6, which is 2.4 volt, right? So now we need to find RS. So RS is given as Vs by Is, and we know that Is is the same as Id, so we can write this as Vs divided by Id, which gives us 2.4 into 16 into 10 to the power minus 3. So this gives us 150 ohm. Okay, so this is the value of Rs, and we can also find VDS from this from the information we have here, though it's not asked. Let's just see how it's done. So VDS is, like the name suggests, again the difference in potential between drain voltage and source voltage. So we found drain voltage as 7.5 and source voltage was 2.4. This is 5.1 volt. Okay. So we also, the last thing that we need to find is R2 and R1. So we know that VG is equal to VDD into R2 divided by R2 plus R1. So we found this by using Thevenin's theorem, right? Where we simplified the two resistors on the left, on the input side, into this form to find gate voltage. So I know that VDD is equal to 15 and this is 1 by 3. So for R2 divided by R2 plus R1 to be 1 by 3, that means R2 has to be in uh, 1 something units and R1 has to be 2 into R2. So we know that we already know that this is the condition and that's been proven here. And we also know that R1 and R2 are in large units like kilo ohm. So we can take R1 to be 200 kilo ohm and R2 to be 100 kilo ohm. So these values of R1, R2 and RS actually satisfy these equations, and most importantly they satisfy the condition that when we put these values of the resistor we get gate voltage to be exactly one third of the of VDD. Alright, so that was the first question. So let's solve another question for this on this topic, and then we'll proceed to the next one. So we have VDD is equal to 5 volt, and along with that I have a resistor here. This is attached to a MOSFET. So yeah, this is done. I have a resistor here and a resistor here. Okay, so this is RS and it's given to be 5 kilo ohm. RD is also given as 5 kilo ohm. R1 is given as 1.6 mega ohm and R2 is given as 3.4 mega ohm. Okay, and then we have threshold voltage as 1 volt. It's said to be in saturation region, and we have K and dash W by L to be 1 milliampere per volt square. Okay, so now what we need to do is we need to find all the voltages at all nodes and the currents flowing through each branch, and then we need to plot the load line. Okay, so the first thing that we do is obviously, since this is a voltage divider bias, we find Vg by using Thevenin's theorem, and we already know that Vg is equal to VDD into R2 divided by R2 plus R1, where we have VDD as 5 volt in this case, and we have R2 to be 3.4, R2 and R1 3.4 plus 1 by 6. So this gives us 5. This 5 cancels, so that gives us VG to be 3.4 volt. Okay, so the next thing that we'll look at is Vs. So we know that Vs is equal to Id into Rs because Id is the same as Is, and we know Rs to be 5 kilo ohm. So Vs is just written as Id into 5. So then we know that Id is equal to half Kn dash half Kn dash into W by L into V overdrive square, right? So we know that the value of this Kn dash W by L is 1. We have half into 1 into VGS minus VT whole square. So let's write VGS as VG minus VS, right? Because that is the potential difference between gate and source. So we found VG sometime back to be 3.4. So we can write 3.4 minus 5 ID, which was the value of Vs, minus the threshold voltage, which is given to be 1, right? So this is Vs, this is Vg, and this is Vt, that is the threshold voltage, right? So now what we get is we actually get a quadratic equation, which is 25 ID square minus 26 ID plus 5.76 is equal to 0. So now what we do is we use the quadratic formula and simplify these questions. So the formula is minus b plus or minus root under b square minus 4ac divided by 2a. So a, b and c are the coefficients of the terms that we have. A is the coefficient of the square term, b is the coefficient of the normal term, and c is the constant term that we have. Okay, so from that we can find the value of what id. So we get two solutions upon solving this. We get id is equal to 0.72 or id is equal to 0.32, right? So that gives us a dilemma, but we know that the current flowing can only be of one magnitude, because you cannot have a current of two different magnitudes flowing into the wire at the same time. So we check whether the value of drain current we got is actually correct by checking the conditions for saturation. So the first thing that we have for saturation is that the gate source voltage should be greater than the threshold voltage. So let's see if that is actually being satisfied. So we know that Vs is equal to 5 into Id. So if Id is 0.72, I get Vs to be 0.72 into 5, which is 3.6 volt, right? So then when I find VGS, I have VG minus VS. VG was found to be 3.4 and VS is 3.6. So like you can see here, VGS is lesser than VT. So this is obviously not the correct value of ID. So let's substitute the other one. For ID is equal to 0.32 milliampere. I get Vs is equal to 5 into ID, which is 5 into 0.32 gives us 1.6 volt. Right. So VGS is 3.4 minus 1.6 gives us 1.8 volt. Right. So with that we found VGS as well, and so the only thing that we are left to do right now is to plot the load line. So I have VD is equal to VDD minus IDRD. So VDD is like we saw 5. ID was 0.32 and RD was given to be 5 kilo ohms. Right, so 0.32 was milliampere and this is kilo ohm. So they basically cancel each other out. Okay, so this gives us 5 minus 1.6, which is 3.4 volt. Okay, so that is VD. So now to find VDS, I need to subtract source voltage from drain voltage. So that gives us 3.4 minus 1.6, which is 1.8 volt. So this is the Q point value, of course, and the value of ID that we found to be 3.2 milliampere. This is the Q point value too. For actually finding the intercepts of y and x axis, we need to find ID max, and ID max is given by VDD divided by RD plus RS. So we know VDD is 5, we know RD and RS are both 5 kilo ohm. So from this we get 0.5 milliampere, and for VDS max, that is basically VDD directly, which is 5 volt, right? So the load line would look something like this, right? So ID max is when VDS is 0 and VDS max is when ID is 0. So the intercepts here will be VDS, and on the y-axis we have ID. So we can see that when VDS is 0, that's when the ID max is at its max, which is 0.5, and then when ID is 0, VDS is at its max, which is 5, right? So this is the load line, and to plot the Q point, we know that VDS is equal to 1.8, and VDS is 1.8. So 1 second, this is wrong. This is 0.5 and this is 5. Yeah, so 1.8 is the location of the Q point, and correspondingly to ID, we have the value of ID to be 0.32, right? So this is the Q point, and this is the load line. So Y intercepts and X intercepts are given by finding the maximum value, and the Q point value is taken using the general equations that we use. So with that, we've come to an end to the DC biasing part of this chapter. So the next topic that we'll talk about is the various capacitances that are present between what do you say, various terminals of the MOSFET. So see, in BJT we had a, we had an emitter, a collector, and a base in between. So like I said, whenever you have two different type of semiconductors joined together like a PN junction, a depletion region forms between both of them, and since there are opposite charges on opposite sides of the region, we tend to get capacitances in them. So like you can see here, let me just go to the main diagram. Like you can see here, there will be a capacitance between the source and the bulk, between the drain and the bulk. So just in case I missed it, the body is also called the bulk, the substrate. So we have like I mentioned, we have a capacitance between the source and the bulk, between drain and the bulk, and we have a capacitance between gate and drain, gate and source, right? So for all of these, we have different formulae. So let's see what is the wait, and I forgot to mention that there is also another capacitance that we have. So this gate is always separated by an insulating layer, which is an oxide. So the very name metal oxide semiconductor field effect transistor comes from this particular oxide. So we also get a capacitance due to this oxide between the gate, and that capacitance depends upon the thickness of that particular oxide. So let's see what all capacitances we have. So the first one, like I mentioned, is the oxide capacitance, and this is given by epsilon oxide divided by T ox. So T ox is the thickness of the oxide, which will be given to us in the question, and epsilon ox is the permittivity of the given medium. So that is given by epsilon O into epsilon R, where epsilon O is 8.85. Sorry, epsilon naught, which is the uh, normal constant we use for permittivity, 10 to the power minus 12 uh, newtons per meter. Right. So this is the first one. The second one is called the overlap capacitance, which is given by C ox into L overall into W. So LOV is the overlap length. Okay, so we have a relation between the overlap capacitance and the overlap length. Then we have a capacitance between gate and source, and this is given by 2 by 3 WL into Cox plus WLOV into Cox. So here LOV is the overlap length, and here L is the length of the entire transistor. It's this W and L are the same parameters that we spoke about in the transistor aspect ratio. It's the width and length of this capacitor respectively. So then we have CGD, which is given by W overlap length into capacitive oxidants. Okay, so that is the capacitance between gate and drain. So now we have capacitance. Now we'll talk about the capacitances between the bulk and the source and the bulk and the drain. So CSB is given by CSB naught divided by root under 1 plus VSB divided by VO. And similarly for uh, drain bulk capacitance, we have dB at 0 and root under 1 plus Vs V D VdB divided by VO. Basically the same formula as here, but instead of source you write drain everywhere, right? So what this CSB of at 0 signifies is what is the value for source and bulk capacitance when the applied voltage is 0, right? And then similarly for CDBO, it's the capacitance between drain and bulk for the same condition. And to find out the present capacitance, we use this formula. Okay, so from this you get direct formula based questions. I know it's a little hard to remember, but these are the easiest ones to score marks in because you just have to remember these formulae. Yes, there is no logic behind them and there is no proper understanding, but this is the only place in this entire module where you have to just blindly cram stuff. So, unfortunately, I'm sorry, you just have to get through this part. So, like I mentioned, there will be direct formula based questions from this part. So, with that, we've come to an end of this oxide capacitances. So, now we'll be moving to uh, just give me a minute. Okay, so now let me go to the cutoff trans. Yeah. So, in the previous lecture, we already saw how we use hybrid pi model to simplify any given circuit. So now I'm not going into too much detail about that. We'll just talk about how that particular model has been applied to a MOSFET and how a few things are different from BJT. Right. So now let's try and calculate the current gain. So for current gain, let's take the KCL at the output node first. So we can see three different currents flowing from the output. So the first one is the output current I naught. So see, since we have short circuited this branch, any resistor parallel to the short circuit becomes useless because if any current flows here, it has two paths, the resistor and the short circuit, and it would flow fully through the short circuit path because it offers zero resistance. So we can just neglect this particular resistance that we have here. So now applying KCL at the node, we have I0 here, then we have GM into VGS here, which is a voltage dependent current source. And then we have the current that flows through capacitance CGD. Right. So let's take that as IGD for now. And then, yeah, obviously, IGD is the potential difference across this terminal divided by the impedance offered by this particular capacitance. So we have VGS divided by 1 by SCGD, right? So upon taking this to the numerator, I have S into CGD into VGS. So now, again, we the same characteristics for BJT are applied here as well. Since this capacitance is very small, we are going to neglect it. And since GM is very high in comparison with GD, we are going to take only the GM term or the transconductance term. So we have I0 or I output to be equal to GM into VGS, right? So this is I output. So now let's find the input current so that we can find current gain. So input current is for that we apply KCL on the input node. So here we can see a current from this side is I1. The current flowing here is VGS divided by the impedance offered here, which is 1 by CGS, and the current flowing through this is see the potential difference across this two is VGS. Sorry. So the current flowing across the potential difference across these two terminals is also VGS, and the impedance offered by them is 1 by SCGD. So we finally get VGS into S into CGS plus CGD. So now what we do is we divide I0 divided by I1. So VGS being the common term is removed. So we have GM divided by S into CGS plus CGT. Right. So that is the final term that we're given here. So the S that we were taking all this while was J omega. Right. So this is the angular frequency into J, which is what we always used to find the impedance of a capacitor. So after writing this, we can write omega further as 2 pi into f, and ft is called the unity gain frequency. It is a value, it's a very particular value of f. Upon taking of this value, you get I output by I input as 1. So by taking this condition, we find unity gain frequency to be uh, GM divided by 2 pi into CGS plus CGD. So I'm not devoting much time to this topic as compared to the BJT lecture because it's almost the same thing. So, and if you are familiar with that, there wouldn't be any issue with this. I will highlight the points which are different alone, so that there is no lack of understanding as to how things actually are different here. Because since the changes are very minor, we need to make sure that we don't miss them. So this is the unity gain frequency in MOSFET. So now we'll talk about the high frequency analysis of MOSFET, or in specific of the common source amplifier, right? So just to compare, I've put up the model of high frequency analysis in BJT, and to the side I've put the model for MOSFET as well. So like you can see, the output side remains the exact same. We have R output, R drain and RC are the same thing, because drain is the equivalent of collector in the MOSFET. So this side is the same, and all we have to do is take these three resistors in parallel. And this side is almost similar except for this part, the Rx and Rpi part. We do not have any specific resistors attached to the gate here, because there is no flow of current through the gate as such. You can think of that as the reason for these two resistors being absent. The R signal and V signal are not a part of the transistor, but is the external attachment. So now what we do is, uh, obviously these three are very easy to simplify, because we just take three resistors in parallel and calculate the equivalent resistance. For this, for the left hand side, we just have to use Thevenin's ones. So let's see. Just to revise, V signal dash will be V signal into RG divided by RG plus R signal, right? Then we have, let's take R dash is given by R signal parallel with RG. Okay, so uh, we reduce this entire circuit into just one voltage source and one resistor in series with the voltage source. Right, so we have simplified this circuit now. This ground doesn't really mean anything. So you can just join this whole thing to avoid confusion. So now let's see the various currents that we have. So IGD is the current that is flowing across this capacitor here. So that is given by VGS minus 0 divided by C GD, right? Okay, so this voltage right here is taken as 0. Sorry, not 0, V0, which is the output voltage. So VGS minus the output voltage divided by the impedance here gives the expression for IGD as this. So the output voltage from this, no, sorry, not from this. See, we know that the output voltage will be the current flowing through this particular resistor, and the current that flows through that resistor is the current from this source, right? So we can write the output voltage as a product of this current into this resistance, and we know that this resistance is the equivalent of the three resistors that were in parallel. So we can simplify this and write the output voltage in this form. So now let's take IGD, that is the current uh, that's that's flowing through the capacitance GD. So GD is this capacitance. So now we are calculating the current that's flowing here. So that is given by SCGD into the output voltage. So we found the output voltage to be this, right? No, sorry. I'm very sorry. This is the output voltage, and this is the VGS, that is the other end of the potential difference. So, no, wait, this is minus, and this is again minus. So, I'm sorry for these errors here. So, this is the potential difference, right? Divided by the impedance. So, after doing this, we do the same thing that we did in a BJT when we had a capacitor like this and another capacitor like this. We reduced the circuit to an equivalent where we had two capacitors in parallel and then found the overall equivalent capacitance by just adding up these two. So for that, again, we need to find the equivalent circuit by equating the current with this voltage and taking an equivalent capacitance. See, basically the concept here is that we are removing this capacitor and placing a new capacitor in parallel, and this change of ours does not affect the rest of the functioning of the rest of the circuit, right? So for that, we write IGD, which is the current flowing here, should be equal to the potential difference divided by the new capacitor, right? So basically the current flowing here should, the value of current should continue to be the same. We have taken a capacitor such that this condition is satisfied. So we get that IGD is equal to S into C equivalent into VJS. And we also found IGD to be equal to this, right? So now what we need to do is we need to equate these two values of uh, the gate to drain current, and that will help us find the relation of C equivalent with the earlier capacitance that we had. So now what we do is we replace the capacitance that we had here with a capacitor in parallel here, and we find the equivalent. We find the equivalent capacitance by just adding the two since they are in parallel and representing it with one capacitor, that is C input, right? So we have the value of V output. We already found the value of V output here, right? So now we need to find the potential difference VGS, that is across this particular capacitor, and we can do that by voltage division rule. So voltage, the source voltage is V signal dash. The impedance across the impedance across which we are trying to find VGS is 1 by SC input, and the total impedance is R signal dash plus 1 by SC input, right? So now V signal dash and R signal dash were not our original values. They were the simplified values we found using Thevenin's, right? So now let us substitute the original values of these things back. So we get Rg by Rg plus R signal into V signal, and this part remains the same, 1 divided by uh, 1 plus this is S R signal dash into C input. Okay, so now we can finally write the entire thing as V output is equal to minus GM gate resistor divided by sum of gate and the signal resistor into the initial voltage signal that we had, the equivalent resistance on the left on the right hand side divided by 1 plus S R signal dash into C input, right? So, like I mentioned before in the BJT lecture, whenever we get anything of the form 1 plus S into a particular term in the denominator, so you can have anything in the numerator, that doesn't matter. As long as you get this term in the denominator, the coefficient of S is called the time constant, which is 1 by omega naught. Okay, and so this entire term here, right? This is called the midband gain. So the formula for AM or midband gain in MOSFET is this. Okay, so now we can write, like I mentioned, the coefficient of S is 1 by omega naught, which is R signal dash into uh, the input capacitance. So we have omega naught is equal to 1 by R signal dash into input capacitance. So finally, like I mentioned, this whole expression here can be written as AM. So we have just written it as AM into 1 divided by 1 plus S by omega naught. Okay. So since omega, this is the value of omega naught, the frequency will be just dividing this entire thing by 2 pi, right? So what this frequency is the frequency on the higher frequency side where the voltage amplification or the voltage gain tends to fall off, right? So this is FH, and I already explained in BJT as to how this circuit works as a low pass filter. So with that, we come to the end of the high frequency response type. So now let's talk about the low frequency response. So wait, this grounding of these terminals doesn't really signify anything. You can just join this part. Okay. So anyway, so again, this is very similar to the BJT part. It's almost the same except for uh, the CS or the source capacitance, which instead of going to the branch on the or to the input side, it's applied on the output side. So, like we always did, we'll take one capacitance at a time and solve all three of them, and then we'll look at the easier method, that is the time constant method, to solve each of them as well. So, first, let's assume that CC1 is the only capacitance that we have, and the others are just ignored. So for that, we short circuit the others. I mean, we open circuit the others. So when we do that, we have VG, that is the potential difference across the gate resistance, to be V signal into RG divided by RG plus R signal plus 1 by SC C1. So this is using the voltage divider rule. And again, like I mentioned, our final aim should be to get something of the form 1 S plus 1 divided by a particular function in the denominator, right? So for doing that, now the only thing that we need to do is we need to take things common outside. So we take RG plus R signal outside and we get 1 plus 1 by SCC1 with Rg plus R signal in the denominator. Now again we take S outside, so that gives us S. We take S outside and it goes to the numerator. So we have S divided by S plus 1 by CC1 into Rg plus R signal, right? So from this we have this part is what we call as omega P1, right? So we know omega P1 is 1 by CC1 into Rg plus R signal. So FP1 will be 2 pi into CC1 into Rg plus R signal. Right. So now this is the different part because this is quite different to the emitter capacitance that we spoke about in BJT. The other two capacitances CC1 and CC2 are almost the same. So there is nothing different about them. So now let's see how this works. So we open circuit all the other capacitances and we just look at this. So the drain current is flowing through 1 by GM and through 1 by the impedance across this capacitance given by SCS, right? So the drain current is given by potential difference across this divided by 1 by GM plus 1 by SC, because this is the total impedance and this is the capacitance. I mean, this is the volt, this is the potential difference. So we are taking 1 by GM here because I mentioned GM is the transconductance. So it's the literal reciprocal of resistance. Like I mentioned, the unit is Siemens. So to find the resistance across this, we take 1 by GM. So we have ID as VG divided by 1 by GM plus 1 by SCS. So again, we need to try and get it in the form of 1 by S plus something or S by S plus something. So here we take 1 by GM outside the bracket first. So that gives us GM by SCS. So again, we take S outside. So that gives us S plus GM by CS, right? So this is the value of omega P1. Sorry, I mean omega P2. So we have omega P2 to be GM by CS, right? So this is a very different expression because in all the others we have only seen 1 divided by particular capacitances and resistances, but here we have dependence on GM or the transconductance. So we have FP2, we just divide omega P2 by a factor of 2 pi, right? So with that we've come to an end of FP2 as well. Uh, then we talk about FP3, where we open circuit CS and CC1 and just have a look at CC2, right? So here I know that the current flowing through this the resistor RL. So see, here we have ID and here we have IO. So the resistor flowing across uh, I'm sorry, I mean the current flowing through this can be given through current division rule as RD divided by RD plus SCC2 plus RL. Right. So in current division rule, what we do is if we have two resistors and we have to find the current flowing through this one, we take let's say R1, R2, we take R1 divided by R1 plus R2 into the original current that was flowing. So since we are trying to find the current that flows through these two, we take this one in the numerator and the entire sum in the denominator. And we also know that the output voltage is the product is a product of the current flowing through the load resistance and the load resistance. So we just found out uh, this current in the form of drain current, the capacitance, and drain resistance. So by substituting all of this, and again we need to take stuff common outside the bracket, we arrive at this expression. So we find omega P3 to be 1 divided by CC2 into RD plus RL. Right. So again, this is very similar to the omega P3 in BJT, and the meaning is the same too. So if you have a board plot, uh, the voltage gain falls off at lower frequencies. So the uppermost point is FP2, and the value of FP2 is much higher than the value of FP1 and FP3. So usually FP1 and FP3 are equal, and FP2 is 10 into their frequency values. So if these are around 10 hertz, the value of FP2 comes out to be 100 hertz. So that is approximately how much larger FP2 is when compared to FP1 and FP3. So like I said, we have a much easier method to find uh, FP1, FP2 and FP3, which is called the time constant method. So here we take we ignore the other capacitances, we take them as open circuits, and we just try to calculate the equivalent resistance across this particular, uh, what do you say, this particular capacitance, right? So upon calculating equivalent resistance here, I get Rg plus R signal. And we discussed that tau is equal to R into C. So here R is Rg plus R signal, while C is Cc1, right? So this is tau, and we know that F, wait, no. We know that omega will be given as uh, T by 2 pi. I mean, no, wait. I'm sorry here. There's a small confusion in the notebook here. So let me just refer to something. Okay. Yeah. So I'm sorry for that. So like I mentioned, so we know F is given as 1 divided by 2 pi into tau. So here we have FP1 as 1 divided by 2 pi into Rg plus R signal into Cc1. So similarly, we take every capacitance circuit, find the equivalent resistance, find the time constant with that, then find the frequency using this formula, which is frequency is equal to 1 by 2 pi into tau, right? So with that, we've come to an end of the time constant method, and with that, we've come to an end of the chapter as well. So I hope you could understand this chapter, and like I said the last time, I hope this helped you in getting some interest towards this subject, because this is one of the core subjects and it will be needed for the rest of your engineering. So it's just better if you develop an interest towards it and not just study it for as something which has to be finished a day before the exam. So I hope this video is, and the previous video in general, is helping you achieve that, and I hope it's also helping you for the exam that you're studying. So we did not do too many questions in this in the video today. We just ensured that all the basics and all the concepts were covered. And wherever I felt questions were necessary to actually understand, because the concept was different, like the DC biasing part, I ensured that some questions were put. So we'll actually conduct a separate question solving session where we'll take questions from both the first module as well as this one, and we'll spend an hour or an hour and a half solving different types of questions. And so if you have if any of you has your own questions, of course you can put it in the comments, and we'll get the solution for it and solve it in the question session that we'll be conducting later on. So thank you for listening, and I hope it was helpful. I'm looking forward to see you all in another day.